Vim's really cool too. I don't remember what the acronym stands for, but it's like, it's an editor that you can use in Linux and like any system. And you don't even need a mouse. And it's like done on the Nope. They set it up so you can just use a keyboard. So it works literally on anything. Yeah. It's really good for like Python and stuff that just uses the terminals.
Alright everybody, so wait, gotta... Okay, so the goal for today is, we got a warning. Stream's bitrate is lower than recommended. What's happening? Everybody's using the Wi-Fi, I guess. I've never gotten that before. I usually have such a good connection. Everybody get off the Wi-Fi. No. He's downloading Altium right now. So the purpose of today, as I said in the announcement, the homework's pushed back till Monday. There is no in-person class on Friday because I have to be down in Seattle by 6:15, and this is not going to happen. But we have the homework. The homework is still good to work your way through. The problems in this homework are interesting because they're not necessarily mathematically that complex. They're conceptually that complex in a way that probably, like when I went through into these homework problems, especially like the problems in the middle, I would start by saying, I think I can do this one way, and then realize that no, I can't do it that way, I got to go another way. So these are design problems, so there's no particular right answer. There's a whole lot of wrong answers, a few right answers, right? But you should expect to kind of, it forces you to think about things differently. You should expect it to be kind of a weird experience, different than the other stuff we've done in this class, the other stuff you've probably done in other classes as well. And you'll find some of you prefer design more than others. And really my goal is, it's not to say are people naturally gifted at design or not, it's if you know you're not gifted at design. Some people are just really good at it. If you're not, then know how to kind of break problems down, know how to compartmentalize your knowledge about existing things, know how to take a problem and define the problem explicitly rather than just sort of keeping it all in your head. And you already do that, most of you know programming. And when you do programming, that's basically the challenge there too. You take a task that's somewhat abstract, and the job of putting that into a format that a machine can solve requires you to be very explicit, requires you to be very precise, very exact. And so there's a similar process you can go through with design. And we went over kind of some of those techniques, right? Doing a number line, showing explicitly, okay, we have values here, they have to map to here. Let's think about what tools do we know that can do these pieces? What are our options? Which one might be better? Which one might be worse? But it's not an exact, it's not a cookbook formula way of doing things. It's also not an encyclopedic way of doing things, where if you just know every single op-amp circuit, you'll necessarily be able to do design, because a lot of it's about pattern recognition. It's about knowing, oh, the way this physical problem is described, boy, this sure sounds like the way this other problem was described. And when we did this other problem, we did it this way. So some of that stuff is not that teachable. It's just kind of experiencing lots of different things and working out. So we are going to work on the homework problems today. I'm going to try to keep it focused just on the homework problems today because we're not going to get another chance to talk about them. And I also so posting the solutions to Franco sometimes causes more problems than it's worth. Not necessarily, right? But just note that this is one old man's way of doing things. And also you'll notice when he does solutions, he does a lot of tildes, how do you pronounce that thing, right? The little about, like, yeah, that's, it's about 7.6, that's about an 8. So let's just call it an 8 from now on. Like, he actually does that in the solution. So just note that that's the care he has towards precision with some of these things. So if you're racking your brain about how do I make 1 over 1 plus 1 over t a nice clean number, he would just call it 1,000 or 1 over 1,000 or something like that. So So don't worry too much about that. So I did want to go over some problems, and I want to make sure at least that I massage, or I tell you, I explain his solution to one of them. I'm trying to go back and see which one it was. Yeah, YouTube doesn't like my bandwidth here, my throughput, but oh yeah, part B to 2.5. 2.5 in general is pretty rough, but part B is particularly weird. And his solution is really messed up because this problem doesn't give you, it gives you ideal input-output resistance, and yet he uses T to describe the characteristics of the op-amp, which is completely, I don't know, whatever. I mean, he should
You didn't ask us to do part B, though.
oh, good. All right. Well, then. All right. Well, this is a lot easier. Good. Okay. So, maybe we should start. Well, is there a place people would like to start? We might just want to start talking about 2.3. Or do people not want to start with that? So let's at least start with the process of 2.3. So 2.3 says, design a circuit to convert a 4 milliamp to 20 milliamp input current to a 0 to 8 volt output voltage. The reference direction of the input source is from ground into your circuit, and the circuit is powered from plus or minus 10 volts, regulated supplies. Okay. Okay, so what do they say? So first of all, the reference, so our problem is, it is a 4 to 20 milliamp input, and that needs to be mapped to a 0 to 8 volt output. So 4 to 20 milliamp input, so if we just do our number line, we could do this side, 100 milliamps, 0, so we have 4 to 20 or so. And then on the other side, we have and so now this thing is going to map so a couple things have to happen. First of all, we have to convert current to voltage for this. So our input is a current, our output has to be a voltage. The other thing is we have to scale. So this 20 minus 4, this 16 milliamp input range has to scale to an 8 volt output range. And then we have to offset this. So this input is 4 to 20. We have to drop that down to 0. Okay, so looking at this problem, my first question is, what circuits do we know that do current to voltage conversion? So, so that's going to be or current to voltage or current to current. So there's two main. So what's the topology of current to voltage converter? That's going to be a shunt, right? So we can look in our book and we can go back to, we forget, oh wait, what the heck was that? Let's see, let's flip back in chapter 1. We're going through this from scratch. Oh, there we go. Oh, I missed it. Oh, still missed it. Should have dog-eared this thing. Okay. Yeah. So that would be current to voltage is given in figure. Uh-oh. Gotta lick my fingers turn these stupid pages. Figure 1.28b is a shunt topology. Input's a current, output is a voltage. So just to remind everybody what that looks like. It looks like this.
I saw it in lecture 6.
Yeah. Okay. And in this circuit, the output voltage here, or the gain of this, we have output voltage. Did they say it explicitly here? I mean, I know what it is. It's going to be negative R times that one. Let's see if they say it explicitly. Trying to give for people who join at home. But anyway, easy analysis of this. We've done this, right? This is what we do for the inverting amplifier. So the op amp is going to produce whatever voltage is necessary such that the current through here is equal to I input. So that's going to be V out equals negative I input times R. So the gain here is going to be negative R. And we don't usually use A actually for a current to voltage gain, but I forget the actual uppercase variable that's usually used, so I'm just going to keep A. So this topology is a great one to start off with. We don't have to use this necessarily. We could convert our current to a voltage and then use a voltage amplifier. We could. What's not good about this topology? So this gets us our gain, right? We need a gain. So let's look at our current to voltage gain. It's going to be 8 minus 0 volts divided by 20 minus 4 milliamps. That's going to be wait, yeah, no. Volts per amp. So ultimately we're going to have a circuit that gets a gain of 50 volts per amp. So what's some downsides about using this topology if this is what we want? Yeah?
Isn't there going to be an impedance problem? Like a problem where like the impedance is of something's too high?
So let's think about the impedance problem. So our input's a current. So for currents we want them to see a very low impedance. And this topology pins this negative terminal to ground, right? So this is always ground. So if I'm this input current, what resistance do I see? I see 0 ohms because this is constantly ground. So even as my current changes, I'm still seeing 0 volts here. So the voltage doesn't change as my current changes. So that's a very low input resistance. So that one's good on the input, but that is a good thing to check. Yeah.
Yep.
Just double check. I got 500 volt amps.
500?
Yeah.
Yeah, that's typical. That's typical of me. I'm off by 10. Whatever, factor of 10 is close enough. Right? It's like I tell my doc with cholesterol, right? It's within an order of magnitude. It's fine. What's the zero? Yeah. So, yeah, that makes sense. 0.5, yeah, okay. 0.5 volts per milliamp. Yeah, okay. But what's the problem here? So we need a gain of 500 now. And so what does this have to be to make a gain of 500? Well, R has to be negative 500 here. So the problem we're going to face with this is it's going to invert. So if we're gonna use this as the core of our circuit, fine. But we also have to then invert and offset. So let's think about each of those tests. Could we add another stage onto this that inverts and offsets?
Yeah.
We could, right? So just a difference amplifier can do that, right? A difference amplifier is great for inverting and offsetting. If we want to invert this, we would just have this be an input to the negative terminal of the difference amplifier, and our offset would be applied to the positive terminal. Can we do inversion or offsetting, though, before we get to the next stage, to keep the next stage simpler? Well, so one nice thing about this op-amp circuit is this terminal is pinned to 0. So this is 0. This is effectively a virtual ground here no matter what. So it could be possible for us to inject an offset current at the input of this circuit. So what current, if we wanted to take 20 to 4 milliamps and convert it to be 16 to 0 milliamps, what current would we have to apply to that negative terminal? We'd have to apply a negative 4 milliamps, right? So we'd have to have somehow a negative 4 milliamps here.
Can we just do that though, or do we have to say where we got that negative 4 milliamps from?
Oh no, yeah, you got to say where you got that. So my question is this: if we wanted to generate negative 4 milliamps here, normally this is very difficult to just generate a negative 4 milliamp current source. But this is a unique situation because this terminal is pinned to 0. So for all intents and purposes, we can assume this is ground. What if we wanted to build it, and what do we have powering this circuit? We have plus or minus 10 volt rails?
Yeah.
Plus or minus 10 volt rails. So we have negative 10 volts. If we have negative 10 volts in ground and we want to make a current of negative 4 milliamps, how can we do that? So all we need to make negative 4 milliamps flowing into this, negative 10, which we have, and then whatever, negative 10 divided by 0.004. Oh, sorry, negative 10 divided by x equals 0.004. What's x? Oh. I don't want to make a 500 mistake again. 2,500? So we could just make this a 2.5K resistor. And you might say, well, come on, how are we supposed to know that's the answer? We've never done this before. And the answer is that's not necessarily the answer. You could have not added the offset there. You could have added the offset at the second stage, and that would have been totally right to do. And actually, it might have been pretty easy to add the offset at the second stage. What's another way we could have added an offset at the second stage that would also invert?
Summing amplifier?
A summing amplifier, yeah. So we could have done a summing amplifier. So this is the solution. This is the way that the book goes, I believe. Yeah, this is the way the book goes. This is the approach they take. Let's do it a different way. So that you'll see a solution that gives it this way. Let's do it a different way. So for this problem, so we know we already did our gain. Our gain has to be, we did from our number line thing, our gain has to be 500 volts per amp. Well, we're not going to be able to get 500 volts per amp, but we can get negative 500 volts per amp, right? So what if we wanted to get negative 500 volts per amp of gain? Then R is going to have to be 500 in this case. So if we chose, and that's just from this gain equation here. So if we chose R is equal to 500, now when I do these problems, I like to write the range of values at the output just so I don't get confused. So if I'm, yeah?
I'm gonna say if you do 500, you do all the gain in that step though, you're gonna hit the rail. Like, you do it that way.
Oh, are you? Oh, sneaky. Sneaky. All right. Yeah, well, that's another reason to write the intermediate value to make sure you don't hit a rail. So if we do a gain of 500 here, what's the 20 going to be? Negative 10, yeah. Negative 10 to the 4 is going to be negative 2. So that might be okay. If we knew these are rail to rail, we might be able to get away with that. It's a little tricky. I would not actually do this though, because yeah, even if it's rail to rail, you're not going to actually get all the way to the rail. So what do we do in this case? If let's say it had gone past the rail, or we're just afraid of this being a 10, then we might say, well, at least this gives us our current to voltage conversion, but let's not put all of our gain here. Let's put half of our gain here. How about that? So let's switch it to half of our gain. And you might say, as we're doing this, this is really frustrating for students because they're like, how are we supposed to know that's what we're supposed to do? And the challenge is, that's not what you're supposed to. You have options, right? The design process is we try something, and when we choose the values, we realize it's slammed into the rail, and we say, oh crap, we got to back up and change this a little bit. So if we switch it to 250, now what's our range of output values? Now it's negative 5 to 1. Negative 5 volts to 1 volt. So, but what did this do? It did our current to voltage conversion. So at least we got that done. So what do we have left to do? Yeah?
Is that negative 5 or negative 1?
It's negative 5 to negative 1. So the 20 milliamps times negative 250 should be negative 5 volts. So our range of output now is negative 5 to negative 1. So now what do we have to do? So now we can sort of redraw our number line. At least now we're dealing with voltage here. So now for this next stage, we have to go negative 6 or whatever. So we got negative 5, negative 1. So we have to that's what we got to do. So now our next stage has to invert, amplify, and offset. And again, the challenge here is there's two circuits we can use to invert, amplify, and offset. Especially if we have the choice of having a positive or negative offset, which we do here because our supply is plus or minus 10 volts. So what two of the primary topologies can we do to do a voltage to voltage conversion that amplifies, has some way of adding an offset, and inverts? So pretty much the summing amplifier and the difference amplifier is the two ways to do it. But another nice thing about this is we now have an ideal voltage output. So this is an ideal voltage, so regardless of RL, regardless of the load, this is going to be good. So we don't have to worry about the second stage. It can be something messy and it's fine. Okay, so first of all, let's see, let's try to do this with a summing amplifier. I like working with a summing amplifier because conceptually it's a lot easier to me than a stupid difference amplifier. So let's say this is one input to a summing amplifier. I'm going to move let me see if somebody's talking to me. Nope. Oh, my computer's about to restart. You sure? Look at that. It does this stuff all the time. It's like the worst time. Yeah, it snuck up on me. It was going to restart in 8 minutes. Class would have been over for the online people. Okay. So if we're doing so now we have negative 5 to 1. What extra gain do we need? We need a gain of 2, right? So ultimately, the next stage is going to have a gain of 2. So this is going to be one input of a summing amplifier. So this is going to be one input. Okay, this one's a question mark. We're going to add that later to do the offset. So if we want this summing amplifier to, for this particular input, if we wanted to multiply it by -2, what does the ratio of these resistors have to be? This resistor has to be twice the size of this resistor, right, for the summing amplifier. The feedback resistor has to be twice this. And so if we're doing a design, if I'm doing a design normally, I would just pick values at this point. I would just pick convenient numbers. So I would say, all right, I know my gain. At this point, if I'm using a summing amplifier for my second stage, the total gain for this signal is going to have to be a -2. So whatever, I'll just say 10K and 5K. Because when we're doing design, we got to pick values somewhere along the line. We got to just bite the bullet and just choose a number. And sometimes when you pick values and you solve for the other values, you realize, well, you know, that kind of sucks. Like, we got the wrong thing here, but oh well. Or, you know, or oh, if we use those values, we got to use a really tiny number or a really big number, and then you go back and change the values that you picked arbitrarily. But for now, whatever, 10K, 5K. So this signal now is getting converted to a current to a voltage. We're adding 250 volts per, -250 volts per milliamp, sorry, volts per amp. Then as it goes through here, we add -2 volts per volt. Total gain of this signal is now 500 volts per amp. Now the question is, what the heck do we do to the offset? The nice thing about adding the offset at the end is we can just calculate our output voltage range and just see what we got to add to it. So our signal here was -5 to -1. And this whole thing was multiplied by -2. So right now, this output is going to be 10 to 2. As is. So how much offset do we have to add to this?
Dude, well, the offset gets converted, right?
Yeah, so we have to take away 2.
We have to put in +2.
Yeah, yeah, so we got to take away 2 volts from the output, but the summing amplifier negates. So we have to have an input. So yeah. So now our question is, all right, we need offset of -2, which means we want to have an input of +2. So which do we have to use, the positive or negative rail at this point? So if we use the negative rail, it's going to be a negative voltage input, which is going to produce a positive sum at the output. So we're going to have to use the positive rail. Yeah, so we're going to have to use 10 volts here. So now the question is, if we want 2 volts of offset and we have a 10K feedback, how do we make this happen? So with a 10, we don't get to choose. We don't get to choose an arbitrary voltage. We have 10 volts in. If we want that 10 volts to produce an offset of -2 volts at the output, then this ratio of resistors is going to have to be, it's going to have to take the 10 and divide it by 5, right? So if we want to scale the signal by 5, this resistor will have to be 5 times bigger than this resistor. So what's happening? We're taking, if we look back at our summing amplifier formula now would say V out equals negative V in times 10K over 5K plus 10 volts times 10K over 50K. So now, as V in, when V in is, let's check our boundaries. When V in is -5, we have -5 times 2, that's 10, plus, sorry, -5 times 2, that's -10. -10 plus, this is a constant 2. So -10 plus 2 is -8, times -1, that's equal to 8. When we have, our input is -1. -1 times 2 is -2. Plus 2, that's 0. -0 is 0. So So by looking at the endpoints, we can verify it. But conceptually, the process we went through is we wanted to do all of our gain right off the bat. If we'd done all of our gain right off the bat, that would have been easy. But then we realized it hit the rail. And actually, I think for this homework problem, if you had just done the full gain at the first stage, you probably would have been. Okay, yeah.
Can you do that RL after the first stage? Like, what is that?
So you don't care. This is just, so RL is just the load resistance, right? And actually, in this case, RL is 5K. I mean, this, if you're this circuit, you see a load of 5K. Because you see a 5K and then this is driven to ground. And what's interesting is we just did two of the exact same circuit topology. Both of these circuits were the shunt-shunt. Shunt-shunt, where the input is current. This is shunt-shunt, where the input is a voltage converted to a current through a 5K resistor. And what's interesting is, so both of these are inverting, we could have either injected a negative current at the input here, or a positive current after the inverting stage. And in this case, we injected a positive current using a positive voltage in a resistor. In this case, we could have injected a negative current using a negative voltage in a resistor. So if you add the offset before the inversion stage, you have to be sure that it's inverted. So what we just did here is different than the way it's done in the book. So the book does this. Yeah, the book does this differently. The book just adds current here to produce the offset, and then it just does a gain, and it does it in a negation. It does an inversion stage to an inverting amplifier, which works too. It's pretty quiet. Everybody's nervous. Everybody always is nervous when we switch to design. But these are good problems to work through. And there's no real way, I mean, working through these problems and thinking about how would I convert a current to a voltage, how would I add offset, this is how you build up the kind of knowledge of how to do these designs. So even as we do these examples in class, don't do it the same way, right? Choose different values when you go through and do this assignment. Think about it, maybe do it a different way. But looking at how this happened, looking at how the book happened should give you stuff to think about for how to do these sorts of designs. Okay. If everybody's okay, I'm going to go on. Yeah.
Just like, so when solving these, is there anything in specific that's just not kosher in terms of analysis? Like, I don't know, when I was solving this problem, like initially I did the voltage conversion initially, and just added a resistor for the current input and then put it into a difference amplifier. But I'm just kind of curious if there's just certain things that are absolutely do not do, or is it where it's still pretty open?
So the biggest no-nos are you can't just use an arbitrary value. Like you can't just say, oh, I need 4 milliamps. Okay, I'm just going to plop in a 4 milliamp current source. That's one thing. So not having any intermediate voltage that goes over the rail voltage. The other big no-nos are making sure that if you don't have a non-ideal output going to a non-ideal input. That's not usually the case. Most of the amplifier topologies we looked at, they either have an ideal input or an ideal output. Actually, they all have an ideal output. So usually, if you use the topologies we've talked about, as soon as you get the input converted through the first stage, every other stage is pretty much fair game. So you don't have to worry too much about impedance, like loading and stuff like that, as long as you're using amplifier topologies. And then it's really just a matter of just dealing with the input. If the input you usually want to just, if you're doing a design just to be safe, give the input an ideal input. So infinite input impedance if it's a voltage, zero input impedance if it's a current. Sometimes the problem will specify, it doesn't need to be that way. But if it's not told to you, I usually like to keep it ideal. So. But again, there's no way to teach this except for just doing an example and then having all of you right now in class go, oh yeah, that works, I guess. Okay, I could see that happening. Yeah. All right, next problem. Oh, does anybody have a different way they approach this, or they thought about this, or yeah?
I'm curious. I tried doing a 500. Well, so I just did a resistor in parallel with the current supply,
then did a voltage follower on the high side of that resistor.
Yeah, so that's not necessarily a no-no, but taking an input and using a resistor to convert a current to a voltage or a voltage to a current, that's normally that's the non-ideal case. So if you're trying to do current to voltage conversion using just a resistor, that's normally, unless you know for sure your input can handle that, that's dangerous to do. But it should be noted that there's the summing amplifier and the difference amplifier and the inverting amplifier all do exactly that. They take an input voltage and convert it to a current using a resistor. And so, so as I say, it's a no-no to use a resistor to convert a voltage to current. I am also, several of the topologies we deal with do precisely that.
Would that be considered incorrect or?
As a first stage, it might. Yeah, as a first stage, it might. So normally when we do these problems, you have to offset, amplify, convert current to voltage. These are your problems. You generally want to choose a first stage that's ideal for the type of input you have. Yeah? Question?
What about for, like, instead of using a summing amplifier, if you were to use a difference, and you could use like a voltage divider to decide like what,
Yeah.
like how much voltage goes into the plus side.
Yeah, so we could use a difference amplifier. The only thing is if you want a signal to invert as it passes through a difference amplifier, it's got to go into the negative, to the subtracting side of the difference amplifier. Yeah. And the math gets a little hairy with difference amplifiers too. Yeah. But it's still doable. But the other thing is you could have had this initial input be a summing amplifier, which is kind of what we do, right? I mean, if you think about, that's kind of what it would have been, is a summing amplifier. Okay, let's do 2.5, or talk about 2.5 at least. 2.5, using an op-amp powered from plus or minus 5 regulated supplies, design a photodetector such that the photodiode current varies from 0 to 10 microamps, V out varies from -4 to 4 volts. No resistance greater than 100 kiloohms can be used. That's the challenge with this one. So this is interesting because this thing says the input is the current from a photodiode, which normally means we have some control over the photodiode. Which normally means we can put it in any direction we want, usually. Kind of depends. So we have a photodiode, which normally they're drawn like this. Well, that's our input to our circuit. And so this photodiode, but normally we can flip it if we want. It depends. We have this photodiode, and it is, what does it say, 0 to 10 microamps. So we have a 0 to 10 microamp input current to our circuit, drawn using a photodiode. And V out needs to be -4 to +4. So in this case, we have to do current to voltage conversion, amplification, and do we have to do offset? Yeah. Same thing we just did in the last problem. And you're going to notice this theme, that every one of these design problems is really just convert, amplify, offset, convert, amplify, offset. There's just different ways to do it. So in this case, we have a very teeny tiny current, though, at the input. So we're definitely going to want to do amplification as a first stage. We also have a current input. What are our circuits that can handle a current input? Well, shunt, shunt, shunt series. The reason we don't tend to use shunt series circuits is because a current output is usually not, I don't like having a current output in my circuit. So I don't like using currents as an input, so I tend not to use like the Howland pump amplifier unless they tell me I have to have a current output. So I usually like to have current to voltage conversion, so usually I like my first stage here to be the shunt. But let's not get too far ahead of ourselves. So back to 0 to 10. Not like that. 0 to 100 milliamps, so it's going to be 0 to 10. And it's going to map to -4 to 4. Okay, so what does our gain have to be here? So the gain has to be 4 minus -4 divided by 10 minus 0 milliamps. That's 8 divided by 10 milliamps. What is that? Oh, microamps. Oh man, I was about to get this. Microamps. So what is that?
800,000.
800,000. So in the circuit that we just had, you know, if we use the same topology, what would this resistor have to be? 800K.
100
I know, right? That's a good loophole, right? Yeah. So, and this is a problem, and if you watch the lecture videos or read through the book, this is a very common challenge in op amps. We don't like to have massive resistive pathways in a circuit. Why? Who watched the video? Everybody's like, we got other classes. I'm going to watch the video the day before the homework's due. The reason we don't like to have massive resistive pathways in our circuit is because these circuits are usually built on a physical board. And that physical board, try as we might to have it all be ideally infinite resistance, it's not infinite resistance. So the surface of our board exists in a universe where the air is filled with carbohydrates and lipids, and they all collect on the surface of things, and they have some finite resistance. Even if it's built on a ceramic substrate with teraohms of resistance, the surface gets junk on it, and that junk conducts electricity. And so we usually can't guarantee that a surface has more than like a gigaohm of resistance if it's a short distance. And so if we start to get massive resistive pathways, one issue is we start to get noise from currents that flow on the surface of our board through the little carbohydrates and from the little sulfur particles from trucks that drive by on the highway and all this other sort of mess. The other issue is when we have very resistive pathways, they're very susceptible to noise. So very resistive loop, all it takes is a tiny little current generated in a very resistive loop to generate a very large voltage noise. So we don't like big resistive pathways. And does anybody know the solution in the videos in the book that we come up with for when we need this to happen and we don't want to have a big resistor? It's the, yeah.
Mr. T?
Mr. T, that's right. Yeah, okay. You get light topical comedy as you go through the videos too, right? You gotta mix it up. Yeah, so let's think about this circuit and just think about what's happening, right? What's happening is, in order to get this massive gain value, so we have a little tiny current, and this circuit is designed to, we have to cancel out that little tiny current. But while canceling out a little tiny current, we want this to produce a really big voltage, plus or minus 4 volts. So the only way to get this thing to have to produce a massive voltage in order to produce a tiny little current is to have a really big resistive feedback pathway. So if the feedback pathway is a massive attenuation, that makes us have a massive gain. But there's other ways to get a massive attenuation without having just a single massive resistor. And one of the ways that the book basically does it is, let's say you took this voltage and rather than converting this voltage directly back into a current, what if you scaled down the voltage? So what if we took this output voltage and we did this voltage and ran it through a voltage divider to make a tinier voltage? And guess what? This could have been like 1K and 100K, and so then or let's say 1K and 99K, and so then this is hacking down our voltage by a factor of 100. And then let's take that voltage, and convert it to a current through this feedback network. So does everybody see conceptually how that works? So that's the idea behind what's called the shunted T network. It's drawn a little funny the way I did it here, but if we take this and we flip it upside down like that, that's the shunted T network. And there's not much to it. So for this problem, the challenge is you have to use this shunted T design. So you're going to have to use the equations in the book for the shunted T. There's not much to them. It's really just plug things in. The biggest challenge students have when designing this is you're going to have to just pick values. I would suggest if you're limited to 100K, I would say make this thing 100K. But then for the rest of it, you're just going to have to kind of pick reasonable resistor values. So you might pick 100K there and pick 10K here and then solve for the value that this needs to be in order to get you the gain that you're looking for. And also in this problem, you might not want to do the full gain again. So you might not want the full gain because it says in this problem you're powered by 5 and negative 5. So the problem is if you do the full gain, instead of being negative 4 and 4, it's going to be 0 to 8 or 0 to negative 8. So again, just like the last problem, you're going to have to do not the full amount of gain right off the bat. Now you might say, well, come on, let's just add a current offset here. So you might say, let's just put 5 volts here and use a 100K resistor. That's not going to work in this case. You can't add the offset here because it's going to take more than a 100K resistor to get, so in this case you need 5 microamps of offset, or negative 5 microamps. You're not going to be able to do that because with 5 volts, 5 microamps, you're back in that situation where you need like a 1,000,000 ohm resistor. So this is really very similar to the last one. The extra challenge here is you can't just, you have to use the shunted T network, the Mr. T circuit. Yeah.
Yeah, the problem in the book, it says use an op amp. So does he solve it with just one op amp?
Use an op amp. No, actually, that's a good question. What does Mr. Franco do? Nope. No, wait, whoa, hold on. Oh, he does.
Does he put a, would you make a difference amplifier?
Ah, okay, he does. Yeah, so this is a challenging problem. So what he does is he adds the offset current here. So he injects offset current here into the T. That's a very non-intuitive solution. I wouldn't expect anybody to do anything that difficult on a midterm, just saying. That's weird. So he does. So he takes a shunted T and then he says, oh, we have to add offset somewhere. We can't add it here, but we can add current here. So he basically says, if you know that you're going to have a maximum of 10 milliamps here, when you have 10 milliamps here, the voltage here is going to be 1 volt or negative 1 volt. So then he says, oh, you need to offset that by, anyway. Yeah, that's a challenge. Do it with 2 op amps. Like, do yourself a favor. Make it similar to what you'd have on a midterm. Do it with 2 op amps. Yeah.
And then in the book it shows the photovoltaic detector circuits, and it has IS labels going down into ground. But it has the diode symbol where the one, you know what I'm saying?
Oh, yeah, so they do like leakage through it like this?
Yeah, exactly. So what's going on there?
Yeah, so, yeah, and that's a detail that if I gave you a question like this on a midterm, I wouldn't leave it up to this. I would just literally say your input is 0 to 10. I would draw it so it's clear. So what's actually happening with photodiodes is a photodiode operates to where, so you all know the reason that current can't flow backwards through a diode junction. It's because you have this band gap, right? You have this barrier to where there's no charge carriers in this little built-in region, like depletion region. Charges accumulate on each side of it, but they don't flow across it. The idea behind a photodiode is a photodiode uses, when the light strikes a photodiode, the light creates a charge carrier within the depletion region of the circuit.
If it does flow the wrong way, I don't think that's why it's
So it does, yeah. So current flow. I mean, you're going to get tons of current flowing this way, but normally the way photodiodes work is you get current when you generate a charge carrier in a depletion region. The positive and negative charges go off to the other side, and it produces a reverse current through the diode. It's weird, but yeah.
So that's why when you get the output from the trans voltage converter, it's not inverted because it was inverted on the input. To the thing.
Yeah, right, exactly. Yeah. I see what you. Yeah, I see what you. Yeah. All right, so we might need to talk about. We didn't get through that much today, so we might need to talk about some of these problems more. I'm going to make it due Monday at midnight, so at least we get a chance to talk about it on Monday in class. We might have to push the midterm back. I heard you guys have more than one midterm next week. Yeah, I heard you have all of the midterms next week. Okay, so this homework will be due Monday. The LTM, make sure the LTM is done Wednesday. We'll do the midterm the week after next week. A week that you should have no midterms at all. Because we need to spend all Monday still talking about this homework, I think. But definitely try to get it mostly done. It's going to be due midnight. You're not going to have all day to work on it Monday.
Can I ask about this problem?
Yeah.
This one, I know in all the examples, they have like an error term. But you know that like for the resistors, or like an error term for the circuit.
Yeah.
In all the problems that I've seen and in the book, they only use a case where only one of the resistors is not exactly right. So how do you know the error term with more than one resistor?
So with all of these, when I analyze these, I don't analyze them with an error term that way. What I do is, if you're given actual values, that's really nice because you can just do a test. So I do, I'll do like solve this with both these inputs being 0.
Okay.
Then solve it with one input being 1 and one input being -1.
Okay.
And that'll give you 2 volts differential input.
Okay.
And so then whatever output you see will be your differential gain. And then solve it with one of them is 0 and one of them is 1. No, solve it with one of them is 0 and one of them is 2, and then it's 1 volt of common mode. Yeah.
Okay. Huh.
So I just do test inputs and just solve it directly. So the nice thing is if you do it with test inputs, it's just solving the equation for the difference amplifier 3 different times.
Okay. And then this, I know that there's like formulas for these that use that error term, and so there's some other way to just like.
Yep, the differential mode gain is just the it's the change in output voltage divided by the differential input voltage.
Okay.
And the common mode is the change in output voltage as a result of the change in common mode input.
Okay.
These are going to be very small, right? So I mean, the common mode input, the common mode gain is going to be very tiny because it's going to be, 1 volt of common mode in the ideal case produces 0 volts of the output. But in this case, it's going to be some slightly non-zero.
Okay, and then ADM should be fairly high.
Yeah, AGM should be fairly big. Yeah. AGM should be very close to the actual gain.
Okay.
I just wanted to, I have, not next Wednesday, LTM's due, the Wednesday after that. It was just in your recent announcement.
Oh no, I did the wrong. Yeah, sorry. Thank you for telling me. Yeah.
So it's
Wow, I did it.
Wednesday.
It's
Okay.
sorry.
Yeah.
So I mentioned I wanted people to know it's not today when I posted it. Sorry, I meant I should. Oh, shoot. That's a
It's a
weird
little
phrase.
below.
When we say next Wednesday, So the Altium assignment though, it's not actually, it's really,
You have to
you
set
can
up
pretty
on the
much do it by
computer.
just following along with what I do in the video that I posted.
Mhm.
The video is an hour long.
Okay.
You can follow along. I yammer a lot too, so.
Well, I think the hardest part is going to be the setup, and I was having a hard time with the VPN. But if you put all of that stuff to go through all of that, I
Yeah.
think it'll be doable.
You can bring it to lab too, so bring it to lab tomorrow. I
Okay.
didn't talk about lab. So bring it to lab tomorrow, and then I will, I can help you get it set up there. Or you can just use the computers in lab. If you do it on the computers in lab,
Yeah.
then there's no setup, so, at
Okay.
all.
I was like, I like logged in on the computer, and it said there wasn't any licenses connected.
That's, so, and that's the, so the PDF that I posted where you have to like type in like this, like, you have to type in this server address, it's like lm-cse.engd, and then a port number. Everybody has to do that, whether it's your personal computer or the computer in the lab. The first time you use it on your account, you gotta enter that stuff too, so.
Okay.
But I mean, while you're logged in the
Yeah.
lab computer too, at lab, I can show you really quick how to do it. But
Okay.
it's in,
Yeah.
it's like page 5 of the PDF that I posted on how to set it up. Yeah.
Okay. Sweet. That'll be good then. I
So,
think
I
that's
don't
the only
think-
part I'm stressed about.
Yeah, I
don't
didn't
think
mean
it'd be bad.
for it being
Yeah.
too time consuming, so it just shouldn't need 2 weeks, but yeah.
Okay.
Yeah.
Cool. Thank you. So it's coming Wednesday.
Yeah, it is supposed to be. I entered the wrong due date.
Oh yeah, I should let you know for the homework, like on the page like with the homework, where there's like a link you click on to either like download the homework or open up that picture of the questions like in a window.
Yeah.
And like that link just like doesn't work anymore. Like it was working like I think earlier today, and then I just clicked on it like.
I think I know what happened. Okay. Yeah, I think I had an extra folder.
Okay.
I had 2 folders that had the problem sets in them.
Mhm.
One of them was imported from a previous class, and I nuked one of them. So. When did I have that due November 3rd? My gosh.
Is that right or no?
No, it's November 22nd. No, it's a fun. The Altium stuff is fun. You're gonna enjoy it.
Yeah.
I was gonna ask, is the LED or the orange and purple LED circuit that you have us build? Are we actually gonna print the board and make those, or?
You can if you want, but no, it's mostly just so it's gonna be you're gonna basically do exactly the op amp I build in the video.
Yeah.
But then you're gonna instead of just disregarding the second op amp that's on the package like I do in the video, you're just gonna build a duplicate circuit that does.
Okay.
So it's
yeah.
it's just a slight tweak of what I do, just so that it's different, so people don't just otherwise people go on cruise control and they just
Yeah,
like
they just go through it.
do exactly what I do. They place it exactly in the position I put it and stuff. Yeah. So yeah, but it's same level of complexity, pretty much the same time, just a little extra stuff.
How does it work? Like we order out to get the circuit boards, like the circuit boards come in and then we still have to like solder everything onto
Yeah.
them? Okay.
But nowadays, the nice thing is too, when you export the layers, if you export the paste layer on top, you can just go to Osh Stencils and order a stencil, and then
Oh.
the process of soldering, it's like $7 for a stencil, and the process of soldering is literally just, you align the stencil with your board, you squeegee paste over it, and then you just put stuff down and put it in the oven. So it's really much easier than doing it by hand, to the point where once students get comfortable with the stencil approach, they prefer it to through-hole soldering. Usually it's like through-hole soldering is really easy and they prefer that, and surface mount sucks, but then once they get the stencil technique down, it's really easy. But just for a class like this, I don't order stencils for people's designs. I recommend they do, but it's just too much. We can't quite do bulk orders with those. So I usually tell students, if you want a stencil, do it, but try to do a bulk order with other students. But it's like more expensive for the stencil than for the PCB.
Okay.
But for or at least our final PCB that we're gonna print and then do, is that through hole or is that gonna be with it?
No, that'll be service now, yeah. So that's what I mean. For that one, I usually strongly recommend students use or get a stencil for
Yeah.
that.
Okay.
We used to be able to cut them here, and then students kind of trashed the stencil cutter and like. Although we have laser, you can do it with laser cutters too. You can do stencils with laser cutters, but it's
Yeah, use the laser cutter down at the makerspace.
yeah. But I just haven't set it up. It might be if a student wanted to get that figured out with like a polyamide sheet, cutting through it, that could be really cool.
But I was gonna ask though, for that, the frequency to voltage converter circuit that I was.
Oh shoot, I don't think I stopped my screen, man. Hold on, sorry. Everything we've been talking about is. Oops,
Lovely
look at that.
recorded.
I know, it's all being recorded.
But I can